Yes, Shivdas, we are live.
All right, great, thanks. So, good morning or good evening, everyone, whichever applies to you. Today we have a speaker, Bob Coecke from Oxford. So, Bob Coecke is chief scientist at Quantinuum. Just a moment. Yeah. So Bob Coecke is chief scientist at Quantinuum, head Quantinuum's Oxford-based quantum NLP and compositional intelligence subteam, distinguished visiting research chair at the Perimeter Institute for Theoretical Physics, emeritus fellow at Wolfson College, Oxford, and visiting fellow at the Computer Science Department and the Mathematical Institute of Oxford University. Previously, he was professor of quantum foundations, logics, and structures at the Department of Computer Science at Oxford University, where he was 20 years and co-founded and led a multidisciplinary quantum group that grew to 50 members, and he supervised close to 70 PhD students. He is still supervising at Oxford and elsewhere, and also still teaching at Oxford's Mathematical Institute. He pioneered categorical quantum mechanics, now in AMS's MSc 2020 classification, ZX calculus, DiscoCat natural language meaning, mathematical foundations for resource theories, quantum natural language processing, and DiscoCert natural language meaning. He co-authored Picturing Quantum Processes with Alex Kissinger, a book providing a fully diagrammatic treatment of quantum theory and its applications. He co-authored Quantum in Pictures with Stefano Goggioso, which does the same, but now accessible to people with no maths background. He co-authored some 200 research papers. He obtained approximately 35 grants, including from NFWO, EPSRC, Leverhulme, EU, ONR, AFO, SR, FQXI, JTF. He still holds grants with the latter two. He is a founding father of the QPL, Quantum Physics and Logic, and ACT, Applied Category Theory Communities, of the Diamond Open Access Journal Compositionality and Cambridge University Press's Applied Category Theory book series. He was the first person to have quantum foundations as part of his academic title. His work has been headlined by various media outlets, including Forbes, New Scientist, Physics World, Computer Weekly. So it's a great pleasure to have him give us this talk today. Thanks a lot, everyone. So over to you, Bob.
Thank you. So I'm going to start screen sharing here. Share screen. That's the one I want to share. Now I'm going to go to view, enter full screen. There we are. Okay. I'm going to move my own face away. I don't want to look at myself all the time. So the title of my talk is From Quantum in Pictures to Practical NLP, Music, and Understandable AI. Let me just clarify first. Where I am. So for a long time, I was a professor at Oxford University in computer science, like Shivdas said. I left around 2020. Well, I mean, like Shiva said, we had a very big group there, like all these people here, almost 50. And in 2020, I left and I became chief scientist at what was then Cambridge Quantum. And in 2021, that changed again because at that point, Cambridge Quantum merged, and now it gets complicated, with part of Honeywell. So Honeywell is a big American company, and part of Honeywell broke away from Honeywell and merged with Cambridge Quantum to become Quantinuum. So Honeywell Quantum Solution and Cambridge Quantum together, they formed Quantinuum, and I'm now chief scientist of that thing. Okay, so this is so beside my global role, I also have my own team in Oxford. So these are the people who are working for me in Oxford. Many of them came actually through my group at the university, and they actually all moved with me, and or came back to me or something like that. This is our logo, and what you see here is a C, like sort of top of the skull is like a C, and it stands for compositional, and the I stands for intelligent and intelligence, and also looks like a Q. So what we are mainly doing is quantum or quantum-inspired compositional intelligence. So it's AI that draws from compositional structure, and you'll understand during my talk what I mean by that. So we've got a nice basement. These are the nice things about having a company. We got this music studio as a team bonus for the development of Lambic. Okay, I'm going back in time now. So this story starts a long time ago when people start to think, what is the right language of quantum? And this was mainly the person who did that, John von Neumann. he founded like a Hilbert space formalism of quantum mechanics. He was the founding father of that. He published it in his book, Mathematische Grundlagen der Quantenmechanik in 1932. But then in 1935, something really funny happened, which you don't see a lot in science. He says, this is 1935, I would like to make a confession which may seem immoral. I do not believe absolutely in Hilbert space no more. So he himself denounced his own quantum formalism 3 years after he actually publicized this in his book. And then the remainder of his career was actually devoted to coming up with alternatives to the quantum formalism. In all fairness, none of these are now really used or have ever been used, but they did all result in a few new fields of mathematics that von Neumann created. But so whatever he tried, it didn't really take over Hilbert space formalism. Now, I should make a comment here. Conceptually, for von Neumann, the most important thing about quantum was measurement process. He said what typifies quantum is what happens when we measure a system. And if we want to come up with a better form of quantum mechanics, we need to first understand quantum measurement better. So that was von Neumann's opinion. So this is Schrödinger. And in 1935, you see the date here on the paper. In 1935, Schrödinger basically wrote the following. So he's talking about what happens when you compose systems in quantum, like putting two systems together. And he says, I would not call that one, but rather the characteristic trait of quantum mechanics, the one that informs its entire departure from classical lines of thought. So Schrödinger had a completely different idea than von Neumann. Schrödinger said it's a composition of systems which is core to quantum, while von Neumann said it's measurement which is core to quantum. Most physicists, most philosophers all followed von Neumann's line of thought, and so nothing was really done with Schrödinger's line of thought. And I think the first time that somebody tried to come up with a new quantum formalism, where composition of systems was the prime actor, was myself and Samson Abramsky in around 2004, where we used category theory, more specifically monoidal categories to start to reaction-mathematics, quantum mechanics, and it's not that important that you know monoidal categories, but basically all it boils down to is you got systems, things you give a name, you could say an electron or a proton or classical data. You got processes, which is maybe an evolution of a system or a classical computation on your data. And then you can compose things in parallel. So you can have more than one system. That's where the composition comes in. And that's all actually what the monoidal category is. It's like processes which are typed by systems and which can be composed both sequentially, like one after the other, and in parallel, like two things going on at the same time. But I mean, category theory, it's not everybody's bread and butter, you know, although these monoidal categories are not that difficult. And therefore, okay, yeah, so this is where the category theory comes from. Monoidal categories are due to Jean Benabou, and then the sort of particular categories we used are actually due to Max Kelly. And then we had to add a dagger. Okay, here is Roger Penrose. He's in Oxford, in the Mathematical Institute. As you know, he won his Nobel Prize for black holes. And beside black holes, if you go back to Penrose's paper, this is, I think, in 1970, you find things like that. So what you see on the left-hand side, are just symbols, then with indices, and like A, B, C, F, G, and then some others. And Penrose really hated this notation, this tensor notation. He hated it. And so it's much more intuitive to draw these things as pictures. You got a tensor like here, this Q, then you just draw it as a box or a blob, and then the indices will just be wires coming in and coming out. And he's doing this for a number of different tensors here. He gives nice diagrammatic representations. So he actually did this when he was an undergraduate student, and he had to learn general relativity as an undergraduate student to start to draw these pictures. And then these people, this is André Joal and Ross Street, they actually realized that Penrose's pictures and the monoidal categories are exactly the same thing. So you can basically substitute category theory with pictures. And so in this paper from 2005, which has a bit of a silly name, Kindergarten Quantum Mechanics, I basically did exactly the same as in the 2004 paper with Samson, but entirely in pictures. So we described things like quantum teleportation and some other things, just using pictures basically. And you'll see a bit more of that. The sort of mathematics that you use in there, it's really silly. It's like here you got like a bent wire, and then you yank the wire, and that turns out to be equivalent to logical deduction in classical logic. So it's a very powerful action. Just you've got a wire which is bent and you yank it. You'll see it in action later. And for example, to give another example from linear algebra, here you got this box, and we sort of bend the output. So we typically think of these pictures as time going from bottom to top. So time flows from bottom to top. So you have this box, and I got this wire coming out on the input, and then I bend it to the output, and then you got this other output which you bend into the input. That actually is the same as taking the transpose of a box. That's equivalent to taking the transpose. And then if you yank the wire, now you see this box rotates 180 degrees. So just rotating 180 degrees, a box is actually equivalent to taking the transpose in this sort of language. And unitarity and all your self-adjoinance, adjoint, all these sort of notions you use from linear algebra and quantum, they all can give very easy representations using these pictures. Okay. So what was the plan? The plan was to do as much as possible of quantum in terms of these pictures. 13 years later, then when we started, there is now this book, Picturing Quantum Processes. It's translated in a number of languages, Chinese, Japanese, Russian, as far as I'm aware. And this is really a full-blown course on quantum computing, quantum foundations, entirely done with pictures. It's entirely done with pictures. So this was actually the statement of success of say that program. Yes, we can replace the Hilbert space formalism with an entirely diagrammatic language. Now we teach. So Alex Kissinger, who actually has taken over my group in Oxford, we've been teaching this in the computer science department as the quantum course since I think 2013 or 2014. So it is a university level course. It's a university level course. You're assumed to know your linear algebra and stuff like that. It's a university level course. So it's not something you can it's not kindergarten quantum mechanics. It's not something you can teach to children or anything like that. And the reason it's so big, we actually teach it in 20 hours. We used to teach it in 20 hours. It's just pictures take a lot of space. That's why it's so big. Okay, 5 years later, and we are now in 2022, 23, really 2023. Now there is this book, Quantum in Pictures. Myself and Stefano is also in my old group still, is also former PhD students. And what this book said, I'm going to read from the back. Maybe you think you don't know enough maths. Oh, okay, now I'm starting. Hello there, want to learn from quantum. Maybe you think you don't know enough maths. Well, that's not a problem. The pictures in this book are a new kind of maths that will teach you all about a quantum world, from quantum teleportation, blah, 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 blah. So really, this is pretty much the same content as the big book, but you don't need to know any maths. It just teaches everything in pictures, nothing more than pictures. And we already have, I mean, it's only out since February, I think, so it's not only a few months out, but we already have reviews from like 10-year-olds who have read it and understand it. And so it is effectively possible now to teach quantum to children using this new approach. I think I'm really sorry, but at the moment, so the way we publish this, because we publish this ourselves as a company, you see, Quantinuum. And of course, we're not a publisher, so we're still trying to figure out how we can best distribute this in the world. And the first thing we did was use some service which Amazon has and which is print on demand. But I believe that in India, it's not available. It's only available in Kindle. I'm not sure. Can anybody confirm? I'm not sure, but we're working on it to actually make it available.
Yes, it is. Yeah, it is available only via Kindle in India.
Yeah, that's what I thought. I mean, we're trying to work on that. A collaborator of me is actually making an Urdu version at the moment of it. He's translating to Urdu because Pakistan is not at all available. But we're working on it. We're working on it. It's a learning process for all of us. Now, what will be available everywhere very soon are the lectures of the entire book. So we have a number of people, we've recorded the entire book as lectures, and they will be freely made available on YouTube. And that's of course available everywhere, as far as I know. I mean, maybe there's some countries where YouTube is censored, I don't know, but I can't imagine why anybody would censor this. Okay, so now let me get you through this a little bit. So I'm going to talk about wires and boxes first. I already started to talk about wires and boxes, but the idea of this language is that systems are represented by a wire. You can think of this wire as where particles live, or where particles flow, or where data flows. So this can be electricity wires, this could be water pipes, this could be like data wires, whatever. And then you got these boxes which are processed direct on wire. So you got an input, a system coming in and a system coming out. They don't have to be the same. You could have a quantum system coming in and, for example, a classical observational data coming out. So this could be a measurement, can be a lot of things. And it doesn't have to be physics, it could be a cooking process or so too. This language just applies to everything. Okay, so you can put these boxes together, and that gives you something which is called a diagram. We call this a diagram, and that's really all the structure there is. Plugging boxes together. Now things become very interesting when you start to build new boxes from ingredients of your theory. And you see so we've got wires. So in particular, we've got like these cup-shaped wires here, and we got these cap-shaped wires. And we're going to treat these cup-shaped wires and these cap-shaped wires themselves as boxes. So the cup-shaped wires, if you look at that box, it has no inputs. It just has two outputs. And that's what we call a state. So a state is a box with only outputs. So a state is something that somebody gives to you, and then you can do stuff with it, like maybe your data on your computer. So the state in this language is something with only outputs. And the thing on top with only inputs, you think of as a test, or some physicists would call this an effect, a test or an effect. And in this case, it's a test on two systems because there's two wires coming in. And now this equation suddenly becomes non-trivial, because on the left-hand side, we've got an incoming wire, but we also got this state. This state of two systems, which actually is supposed to represent the Bell state. So this cup-shaped wire is like the Bell state. Huh? And then we've got this effect or test, and you have to think of this as the Bell test or the Bell effect. It's measuring whether these two systems are actually in a Bell state, checking whether they're actually in a Bell state. And so this is a process, and there's actually in the middle, there's like three systems involved. So it's a non-trivial thing. So just yanking this wire straight becomes a non-trivial equation. And here I was talking earlier about transposed, like sliding a box like that along this cup-shaped wire. That's really like taking the transpose. That's really like taking the transpose, sliding this box along cup-shaped wire. And now, okay, and without doing anything, we actually just invented teleportation. We just invented quantum teleportation. So what you see here is, I mean, this is an ugly drawn galaxy. It didn't appear in the book because it was too ugly. We did planets instead. So, but yeah, it's an old slide. And what you see is you go on the left-hand side, you got this box with a diamond, and then you got also a cup-shaped wire, which is connecting these two sides of the galaxy. And then, say on the left-hand side, say Alice's side, if she does this cap-shaped test or effect, then you see we can just push this box all the way through the other side along that wire, because you're allowed to slide boxes along wire. There is no input, so nothing comes out. You can just slide, and this is really quantum teleportation. This is post-selected quantum teleportation. So if you do these actions, you share a Bell state. On Alice's side, you do this Bell test. Then actually, if you're lucky and you get the right outcome for your Bell measurement, which is the Bell test, then your box on the left will actually end up on the right. And that's post-selected quantum teleportation. That's really what Zeilinger did. And he got his Nobel Prize for it. They do post-selected stuff in photonics. He did this in 92. Actually, Zeilinger asked me to sign his copy of Quantum in Pictures a few weeks ago. He came to me and asked for me to sign it. But that was kind of nice. I've known him for a long time, and he's been always a really big fan of, from day one, he was a big fan of these diagrams, Zeilinger. So, okay, as we know, if you know in teleportation, of course, you may be unlucky when you try to do your measurement, your Bell measurement, and you don't get a Bell state, but you get one of the other Bell states. Worst terminology ever, of course. One thing is called Bell state, and then the four are also called Bell states. So if you get the wrong one, it doesn't matter, because you can represent this like I do here by this box, which is one of the Paulis, really, which is one of the Paulis. We'll see later what this is. And then you just take a phone call. Alice calls, here we call them Andrea and Blaise. Andrea calls Blaise. And so Blaise can do the appropriate correction so that the teleportation is still. So you have to think of these two boxes as mutually inverse to each other, as canceling each other's out. Anyway, but this is a bit ugly. This is a bit ugly in the sense that we have to draw this weird telephone wire there. It would be much nicer if a telephone wire is itself part of the language of diagrams. And we can do that. We can do that. And for that, you need a little bit more. You need something we call spiders. So to understand what a spider is, you need to actually first understand what a wire is. So what is a wire? A wire is a thing with two endpoints. That's what a wire is. It's a thing with two endpoints that are connected to each other. And what is the behavior of a wire? The behavior of a wire is if you glue two wires together, like you take one endpoint of one wire and another endpoint from the other wire, and you glue them together, then you get again a wire. If you got an extension lead, say an electricity extension lead, and you just plug them together, you just got another extension lead, just one extension lead. So it's there's not much you can do with wires except like making wires. Now spiders are a little bit more interesting. So this is a spider. It's like a wire, but instead of only two ends, it can have an arbitrary number of ends. So here you see a spider with 8 legs. This could be also 7 legs or 1 leg or no legs or 100 legs. That's all okay. So it doesn't matter, any number of legs. And what do spiders do? What is the behavior of spiders? Well, it's pretty much the same as the behavior of wires. If you glue two spiders together, you get again a spider. But now not necessarily the same one because the number of legs may be different. So that's all you need to know. Now, I mean, this looks really silly. This looks really silly as an equation, but a very remarkable fact about this particular equation is that, and that's something we proved like somewhere in 2009, that if you interpret these things as linear maps, so a leg of a spider thing, that's a qubit. Like each leg corresponds with a qubit. So basically the input of a spider would be a number of qubits tensed together, namely, like for example, the one on the right hand side, this would be 3 qubits tensed together. The output would be 4 qubits tensed together. And if you then ask these spiders to be linear maps from say 3 qubits to 4 qubits that obey this equation, then you can show that they're in one-to-one correspondence with orthonormal bases. So this is an axiomatization of orthonormal bases. It's remarkable. You don't see the notion of sum, you don't see anything like linear combinations, but this is a way to define orthonormal bases in a completely different way than it's usually done. You find this in a paper on a new description of orthogonal bases, I think. Yeah. So it's so whenever you see a family of spiders, you have to think orthonormal bases. So this is an orthonormal basis. Okay, we see 2 colors of spiders now. So this really means 2 orthonormal bases. You got the green orthonormal base and you got the red orthonormal bases. And what happens here is if these 2 spiders, the red and the green one, are connected by 2 wires, then they actually vanish. Then they vanish. That's a condition which you pose on certain. This is a condition which you pose on certain spiders. This is how we define the red spider relative to the green spider by this equation. And if you think of red and green as orthonormal bases, then what this equation expresses is that these bases are mutually unbiased, or in older terminology, complementary. So they're complementary bases or mutually unbiased bases if they satisfy this equation. So this would be, for example, so the way to think about this is, for example, that you got the green to be the Z basis, what people call the Z basis, and the red to be the X basis. So the green corresponds with 0, 1, and the red corresponds with plus and minus basis. And then this equation makes sure that they behave like that. So, okay, so we got now 2 equations. We got this equation on spiders of the same color fusing together, spider of different colors losing their legs if they're connected by 2, or 4, or 6, or 8, or whatever, of course. And now we can use this to compute. So what you see here is supposed to be a quantum circuit, or even a classical circuit, because there's no phases, but it's a circuit. And it turns out if you connect the spider of the Z basis with the spider to the X basis, like I just did here, then you actually get exactly the C0 gate. You may find it weird that we've got this horizontal wire, but it actually doesn't matter how you connect them, whether you put first the green or first the red, it doesn't matter. It's always the same. So that's why we put this wire actually effectively horizontal. And so what you see there are 3 C0 gates. You see 3 C0 gates. The green dot is the control, and the red dot is actually where you potentially negate if your control bit is 1. Okay, so we've got a circuit here, 3 C0 gates, 3 qubits, say 3 C0 gates. Can we now use our spiders to simplify this? Okay, we see 2 red spiders together and 3 green spiders, so we can just fuse them. See, we fuse all these red and these green ones together. Boom. Now we see there are 2 wires between the red and the green, so they fall away. So now on the left-hand side we got a wire with 2 endpoints, so that's just a wire, really. So we just showed, it's a very trivial computation, but we showed that this circuit can actually be simplified to this circuit. It's a very simple computation. I mean, I'm making it so simple just for insightfulness. I can get through again. So green fuses together and red fuse together. See this here. And then these 2 wires between red and green vanish. Okay, so this is a very silly example. However, this methodology to simplify circuits using these spiders and all that is the state of the art for quantum circuit optimization. This is part of the best way people can now simplify circuits. And if, for example, go to the compiler, our compiler, which is called Ticket, then inside the compiler, this is happening. This is how circuits are being simplified and optimized using this spider technique. So the key issue here, what happens really is usually in circuits, quantum circuits, you would treat a C0 gate as a monolithic thing that exists on its own. What we do here is we break it in 2 pieces. We break a C0 gate in 2 pieces, which are 2 spiders, a red and a green one. And that's what gives you the computational power, by breaking things in smaller things, which are much simpler to work with. That's effectively what's happening here. Okay? So now, chapter 6. This is just to show you something that's non-trivial. So in chapter 6 of Quantum in Picture, you basically find quantum non-legality, which is what the Nobel Prize was given for, to Zeilinger and to others, of course. Okay, so I'm going to be not in detail, but I'm just going to give you a sense on how you prove quantum non-locality in diagrams. Basically, this is what's called the GHZ scenario. Greenberger, Horn, Zeilinger scenario. So what you've gotten there is you've got 4 different measurement situations on a GHZ state. So at the bottom of the picture, this double red dot with these double wires coming out, that's actually a GHZ state. I didn't say this before, but in this picture, you have both quantum and classical at the same time. When you see a single wire, it's classical. When you see a double wire, it's quantum. That's the way and so you see these green dots, they go from 2 wires to 1 wire. So they're quantum measurements. They're measurements. So focus on the picture on the left-hand side. So you get these 4 scenarios. If you look at the left-hand side, what you basically do is you got this GHZ state, this red state, then you got this red dot, which is actually nothing. It's like 0 phase. It's supposed to be a 0 phase, so it does nothing. And then you got these 3 measurements. Huh? Now next to it, you got like, again, GHZ state, but you see now you've got these 2 red dots with 90 degrees on it. So you have to think of this as a rotation along the x-axis, rotation along the x-axis of 90 degrees. So you're actually doing a different measurement. You're not doing the same measurement anymore. And you see then there are these 2 other scenarios which do different rotations on different systems. So basically what you then, so basically there is an equation which allows you to commute the green and the red dots through each other. And so basically what happens is all these red dots, they actually end up together at the top and they get added on. So you get like 180 and another time 180, another time 180. So you get 180 degrees. So you'll up there, you will get a red dot with 180 degrees. I'm not going to go through the calculation, but that's what you get. Now this next picture is the expression of the fact that there is a local hidden variable model. So for each of these measurements, you see I've got 3 measurements always on these states, and we either do a 0 phase or a 9 phase. So we're basically doing 6 different measurements, and those are the variables, the hidden variables for the 6 different measurements, which are copied to the different measurement scenarios. So this green dot is really copying to the different measurement scenarios, and this red dot is actually a parity test. So we did a parity test in the quantum scenario, and here we do a parity test. Now you see between all these green and red dots, there's 2 wires. So they just go away. So you basically end up with a red dot with nothing. So in the quantum case, you get a red dot with 180 degrees, which actually is the 1 bit, the bit 1. And in the local variable measure, you get this red dot with a 0. This is actually the 0 bit. So here you get 1, here you get 0. It's a contradiction. Quantum mechanics does not admit a local invariable model. That's what you can prove just with these pictures. This is what you find in our book, Quantum in Pictures. So we prove non-locality just using these wires. Okay, so I mean, it's a very important event this year's Nobel Prize, because it's really the Nobel Prize for Quantum Foundation. They try to sort of phrase it as this is a quantum computing Nobel Prize. No, this was a Nobel Prize for quantum foundations and nothing else. And so I wrote this blog post about how important it was that quantum foundations finally came out of stealth, because it used to have a bad reputation. And I did my PhD in the 90s, it had a bad reputation. And now everybody knows that it has given rise to the field of quantum computing. And what I'm talking about is new languages, that's quantum foundations. Like Shiba said, I was actually the first quantum foundation, the first person in the world with the title Professor of Quantum Foundations. Okay, yeah, I mentioned like the 10-year-old review. This was somewhere on Facebook. Alexander Gika at the age of 10. He says very clear, very well structured, and easier to understand than science videos on YouTube. So that's his dad, actually. His dad is laughing because I think it's really funny that Alexander formulated it like that. Okay, so now, I mean, we are scientists, and it's one thing to claim. It's one thing to claim that teenagers or children can read this book, but we want proof. So at the moment, in collaboration with IBM and Oxford University, Stefano and Alex, and ourselves as Core Quantinium, we're going to demonstrate that using these pictures, teenagers can actually outperform Oxford University students in a quantum exam. The Oxford students will get normal quantum mechanics, Hilbert space. The teenagers get the wires and the spiders, and they're going to get the same sets of equations. And these will be questions like, okay, simplify a circuit and stuff like that. You know, like very relevant questions for quantum computing. And then we're going to see who wins, and we're pretty sure that the kids are going to do better than the Oxford University students. We're pretty sure of that. Okay, so what I've been talking about now mostly is something that's called ZX calculus. So that's the name by which this Reed and these Gret spiders go. And this goes back to 2007. Ross Duncan, who's the head of software at Quantinium. Many of my former collaborators are all at Quantinium. Let's see that. So he's now the head of software at Quantinium. And we came up with this thing called ZX calculus. And it really took a lot of time for people to pick this up. And for many reasons, there's many sociological reasons why you could say that people were resistant to it. I think there was like an ego and a macho thing going on there, because people didn't believe that something that looked so simple could be useful in any way. People couldn't believe it. Now things have completely changed. Now it's this is an example from a paper from PsyQuantum. So PsyQuantum does photonic quantum computing. The ZX calculus is an immensely useful graphical language for linear math between qubits that can be used to describe and optimize quantum. Okay, so as it turns out now, all the photonic quantum computing companies are using ZX calculus, and for example in PsyQuantum, it is the main language. It is the main language they use. Can go to all these PsyQuantum papers. They all use ZX calculus to describe their photonic circuits and all that. So they all use it now. All the photonic people like Quandela, I know Xanadu just hired the ZX person, so it's clear what they're going to do. They're all using this diagrammatic language. So that's the first place where it's not just useful, it's the quantum formalism that they use. Okay, so now, I mean, this is the cherry on the cake. You see It's a paper about the X calculus, and you see the last author is a man called Peter Shor. So the Shor who basically started the whole quantum computing revolution with factoring algorithm. And so they say our main tool is the ZX calculus. So and Shor is advocating using ZX calculus for all error correction. I mean, in Google, Craig Gidney is doing all the error correction also with ZX calculus in Google. And IBM is actually promoting ZX calculus in their Qiskit fans. So it's becoming very dominant. So these are the companies I'm aware of who are now using ZX calculus in some way or another. So these are not just quantum computing companies, they are like regular companies and stuff like that. You see BBC, Merck, Wolfram has been publishing about ZX calculus. So you see there's a lot of companies. NASA, yeah, and there's people working on ZX calculus in NASA. So yeah. So but it took a long time for it. It's interesting. It really became widespread with the start of quantum industry. Because in industry, people use things that are useful. In academics, there is no such a validation mechanism. In academics do what they think is important, which may not be the right thing or the best thing. But the mentality in academia is good science is done by good scientists. And so that there is no sort of other validation to why you would use something or something not. And it's really industry has been pushing the use of these diagrams. And it's remarkable because these are pictures from the 2007 paper. And this effectively, what you see there on these pictures, you see on top the circuit simplification, which people now are using in the compilers, which is the state of the art. So it was already there. And then on the bottom is actually fusion-based, measurement-based quantum computing, exactly what PsiQuantum is doing and exactly why they're needing the diagrams now. So this was all in our first 2007 paper, but people just didn't pick up. So, okay, question, why is this language so powerful? Why is this language so powerful? Well, what these people proved, and most of them are former PhD students, many of them are former PhD students of me, what they proved is that any equation you can derive using linear algebra in Hilbert space, any equation you can derive using linear algebra in Hilbert space, you can also derive using these spiders and these diagrams. So there is no equation, there are no more equations you can derive in Hilbert space using linear algebra than you can derive using this diagrammatic language. So it's what logicians call complete. Of course, it's universal. It's universal. Universal just means that you can write down any matrix as a spiders. Any matrix can be written down as spiders. But completeness is much stronger. It means any equation you can derive between such things. If you can derive in Hilbert space, you can also derive it just using the spiders and spider rewriting. So it's a very powerful. So it's a very powerful system. It's an equational axiomatization of Hilbert space. So it's truly an alternative to the Hilbert space formulas. Okay, and now something completely different. So this is Jim Lambeck. Jim Lambeck was an important mathematician and an important category theoretician, but he was also a mathematical linguist. Probably one of the most prominent mathematical linguists ever. In 1956, he published a paper called The Mathematics of Sentence Structure. And basically what he came up with there is a little algebraic system, a piece of algebra that helps you verify where a sentence is grammatically correct form. So that's what Jim Lambeck he built. There was some previous work, but his work is sort of made it really come to the forefront, and then people like Chomsky elaborated on it, and so yeah, he's really a father of mathematical linguistics, Jim Lambeck. And now let's go back to Montreal, 2005. So I was at some point a postdoc in Montreal in 2001, I think, before I came to Oxford. And in 2005, I just had come up with this paper, Kindergarten Quantum Mechanics, and I wanted to explain these people there, the category theory group, about how cool it is that you can use these diagrams to derive things like teleportation. I was explaining that. I was there explaining quantum teleportation. And then Jim was in the audience. And when Jim saw me, he said, "Bob, this is grammar." I said, "No, Jim, this is physics. This is quantum physics. This is teleportation." He said, "No, Bob, this is exactly grammar." And he was right. He was right. As it turns out, if you think of the categorical structure of these cups and caps and all that, and which I've been explaining to you, this is exactly the same mathematical structure as Jim, not in 56, but in 99, had come up with as some sort of algebraic gadget to verify grammatical correctness. So he had his theory in 56, and then in 1999 he came up with a different theory, which in a way was simpler. And this exactly matched the R diagrams. They're the same kind of categories. They're the categorical definition of both the grammatical gadget, the grammatical algebra, and the quantum thing with cups and caps and stuff like that for teleportation. It's the same. It's the same maths. It's the same maths. Which is really interesting. But I mean, at the time, I kind of considered this a sort of a freak thing. I mean, I was just starting to develop this categorical quantum mechanics. I had no time to think about linguistics and stuff like that. I had no time for that. But then 3 years later, in Oxford, I had two colleagues there. So one of them, they actually knew the grammar mathematics. They knew this Lambek stuff because Lambek had asked her to actually, Lambek had asked her to develop that system for a specific case of Persian. So he wanted to you still have to come up with types and stuff like that for each, and they're different in each language, the types, and then she had developed this for Persian. So she knew this Lambek stuff. I'll explain a little bit how it works. So basically, you got a bunch of symbols which correspond with basic grammatical type. So noun is a basic grammatical type. A sentence is a basic grammatical type. A transitive verb is not a basic grammatical type because a transitive verb can't really live on its own. It needs an object and a subject. And the way you encode this is like by this thing you see this -1 n, s, and -1. So that is actually the type of a transitive verb. And the -1, you have to think of like an inverse in a group. It basically is saying, I want a noun on the left so that it cancels out with my -1 noun, and I want the noun on the right so it cancels out with my noun -1. And you see that's the calculation which you see at the bottom. So you basically got a noun, a transitive verb, and a noun. And then after canceling out, you end up with a sentence, and that means that a noun, a transitive verb, and a noun together make a correct sentence. They make a valid sentence. Now, what is it? Now, okay, that's sort of how it works, and it works for any kind of sentence, however big. It works in any kind of language. Sometimes, for example, in a different language, the noun, the type of transitive verb could be different because maybe the subject is not, maybe subject and object come after the verb or come before the verb. This is different, but you can always come up with a system that takes care of that. It always works. The more important thing for us now is to actually realize that such a calculation, like I just did, can actually be represented by a diagram. So you see the noun and the -1 noun here, and they cancel out, and we can represent this by a cup-shaped wire. The sentence goes through, and then we got noun -1 and noun, and again, we can represent this canceling out by a cup-shaped wire. So this calculation of correctness, grammatical correctness, can actually be represented by a diagram. Okay, so that's all that. Now, okay, there's a lot of machine learning going on now for natural language processing, of course, like with all these GPTs and chat GPT and stuff like that. So in 2007, this was actually still an academic discipline. This hadn't gone outside of universities yet, really. So, and Steve Clark, who's now our head of AI, he actually was studying the representation of words as vectors. That's what all these GPTs and stuff like that do. They represent meanings by vectors, and he was starting to study this. And so on the one hand, we had Merluge, who knew about like this grammar stuff, and on the other hand, we had Steve, who was representing meaning by vectors, word meanings by vectors. And then a natural question is, can we combine meaning and grammar? We as humans, we combine meaning and grammar because if we know the meaning of words and a sentence is grammatically well formed, then we understand the meaning of a sentence. So we can derive the meaning of a sentence typically from the meaning of its words and its grammatical structure. We as humans, we can do that. When you hear a sentence you never hear before, but you know the words and the sentence is grammatically correct, you understand the sentence. That's what we as humans do. So it's a very natural question to ask, can we do this mathematically, combining meaning? Now here, these are vectors, and then grammar, which are these grammatical structures. Can we combine this? And this was an open question. Nobody has ever done that, combining meaning and grammar in a compositional way. And I mean, I knew how to do it. I knew how to do it because Jim had told me. basically what we've got here is we've got a new quantum formalism, and the wires and all that looks exactly like grammar. Now, what flows in the wires in quantum mechanics, it's vectors. It's vectors. It's vectors in Hilbert space, quantum states. That's what lives inside the wires. So we can basically use that formalism and have these meaning vectors live in the wires, and then have the cups and a cap correspond to the grammatical structure. So we have this quantum formalism ready to actually combine meaning and grammar. So we did this in this paper. We actually had a shorter paper in 2007, so 2008, I think. So, but this is the big paper in which we published this, and this is the idea. This is an algorithm. So what you see on top are representations of meaning of words. So you got a vector for Alice, we got a vector for H, we got a vector for Bob. What you see on the top, bottom is actually this grammatical structure. This is exactly the diagram we wrote, which corresponds to the grammatical structure. Now, by plugging these two together, we actually spit something out, which is supposed to be the meaning of a sentence. So it's almost like you teleport Bob through H, and then H is sort of like an entangling gate, which connects Alice and Bob together in that sort of relationship. It could also be a marriage relationship, could be another relationship, but this is the way to think about it. And we did lots of experiments, and it worked. The theory worked, the theory was right. This is effectively how word meanings interact grammatically. And then you can do things like, for example, you can compute an inner product. You see this is a bracket on his side. Alice does not like Bob is one sentence, Alice hates Bob, and then we can check if these sentences are close to each other in meaning. And that we do this by just taking the inner product. We just take the product of the sentences. So, and then, I mean, I'm not going to go into this because it's getting late, but also spiders start to play an important role. For example, for representing relative pronouns, use spiders. So a lot of the stuff we had developed specifically for quantum, we suddenly were using to understand natural language and to compute things with natural language. Okay, so I mean, at the time when this just came out, I told my co-authors, never mention quantum. Because if anybody's going to think that somebody that using quantum formalism for language meaning would be a good idea, then they probably brand you to be a crackpot. And I didn't want to be branded a crackpot, so I tried to avoid. We said, oh no, we just have an algorithm for language. Let's not mention quantum too much. And then the public media came out, quantum linguistics, quantum linguist, quantum mechanical words. So we got completely branded as quantum linguists and stuff like that. I'm talking now, you can see the dates, 2013, 2010, 2013. So there were no quantum computers yet. There weren't any quantum computers yet. However, now people are very interested in quantum computers because there's many problems in chemistry and materials which are really, really hard to simulate on a classical machine. That's what Feynman said. Like, if you want to actually compute quantum, like chemistry or materials where you need quantum to compute things, then you better do it on a quantum computer because classically it's going to be exponentially expensive. We are in exactly the same situation. We've got a nice theory for language, compositional theory of language meaning, but it's vectors and tensor products, so it's hard. So as a tensor network, this is hard. It's hard to compute. Now, so we took a little bit of a break in 2013 because our theory worked very well, but it didn't really scale very, very well. It didn't scale very well with classical computers because this tensor became too big and too hard. However, around 2016-ish, so the first quantum computing company started to become sort of more active, like Rigetti and things like that. And I had this PhD student, Will Zhang, and I later moved to Rigetti. And we actually took the idea for the first time serious to stick this language model on a quantum computer. So we checked, is there any quantum advantage to doing that? And then we discovered that we got algorithmic advantage. But this was still theory. This was still theory. Then in 2020, Elias Kahn, the then CEO of Cambridge Quantum, came to me and said, Bob, you really need to take this quantum natural language processing serious. I'm going to give some money, you can hire some people, and I want you to do that. And so we effectively did question answering using our new language theory on a quantum computer for the first time, I think, in early 2020, February 2020, for the first time, anybody did like quantum natural language processing, like processing natural language on a quantum computer. Then this was a very small experiment. Then we did a bigger experiment, and then we actually made our software very clean and very tight and all that, and we released it as open source software. So everybody can now do quantum natural language processing on one of the available IBM quantum computers. Because our software is available. It's called Lambec. It's called Lambec with a Q. You know where the name comes from Jim. And yeah, it's a pity that he's not here anymore to see this for himself. But I talked to his children, and they were very excited about this idea that it actually, they said, incredible that the last thing you would have imagined are that sort of appearing in Forbes. And well, so this is the paper where we describe how you can use Lambec to do quantum natural language processing yourself. And so others have started to do that. This is a team from IBM. They've then been using Coecke, which is our language theory, our first language theory, and they've done sentiment analysis experiments. And then that's another team at IBM. They actually used our thing to generate language. They want to generate rather than analyze. They have actually written if you want to read more about what I'm talking, they wrote a very nice blog. These IBM people, an introduction to quantum natural language processing, and it's mainly the stuff we have been doing that's in there. And one of the things we have been doing, which is described in there, is we basically took our language tool, we took out linguistic grammar, and instead we put in musical grammar. You can develop grammars for music, and so we have another software which is called Quanthoven. And Quanthoven basically uses exactly the same sort of machinery, but you can use it to classify or generate music. I mean, so as a joke, we produced a few pieces of music. This is together with Eduardo Miranda, who's actually a composer. And we ended up #1 in the classical charts with Bob's Cigar Bus. It's effectively music generated with a quantum computer, which is pretty incredible if you think about it. I think it's time. So I don't know. This is Brian Eno, who's a very famous producer, and he's very interested in our quantum music too. I think I'm going to leave it here. Yeah. So I'm just going to inside Lambec. What happens is basically we take this linguistic theory, and then we start to pull spiders out, and we turn this into a quantum circuit. So this is language as a quantum circuit. I see we represented it in ZX calculus with all these phases and spiders. So that's what Lambec does. It really uses this ZX calculus and stuff too. It takes language and it turns it into quantum circuit, and then you do some then you can do some training and stuff like that, using some classical optimizers. And I'm going to stop. We're now working with a new theory of language, which is actually more about text, but I'm not going to go into that. I think I'm going to leave it here. I'm going to skip all of that stuff. And I end here. Thank you.
Thanks a lot, Bob. So any questions from anyone? So Bob?
Can I ask a question?
Yeah, sure.
Okay, thank you very much, Bob, for this wonderful talk. It was very interesting. Maybe you mentioned, I mean, of course, you mentioned that the latter part of your talk, but I still want to ask you again and just understand it clearly that whether quantum natural language processing has shown an evident quantum advantage from the NISQ devices. I mean, when you use the NISQ devices to do some quantum natural language processing, did it show some evident quantum advantage compared to the classical natural language processing?
Yeah, so that's a very good question. There's like a few different ways you can answer that. So theoretically, we knew that there was going to be advantage since 2016, but of course that would need bigger machines than are available now. Mm-hmm. However, we are expecting. And this is not using this Disco cat anymore. This is a new theory, Disco set. We are hoping, I'm pretty sure, that with our new generation hardware, which we have within the year, so the former Honeywell hardware, with the new generation hardware we're going to have, that we will be able to demonstrate meaningful quantum advantage for the first time. So far, quantum advantage has not been demonstrated in a meaningful way. It's always been like silly problems nobody cares about. So this will be a meaningful, we're hoping within the year, meaningful quantum advantage. So So, I mean, I didn't talk about it, like, but we have a new theory of language, which is for text. And basically, you have to think of a text as an evolution, as a quantum evolution. So a progressing story, the story that progresses, the meaning that evolves, will be like a quantum evolution. So we're expecting the same kind of advantage as you would have for chemistry, because it's the same. It's really literally simulating quantum systems. That our natural language processing will literally be simulating quantum systems. So you're expecting this is going to be really hard on classical hardware. You can't do this. And you know what's happening now? I mean, there are two kinds of advantages we have. So one advantage is the speed up. The other advantage is the complete lack of interpretability of classical NLP. So today, I don't know whether you've seen the news, but today on BBC News, Jeffrey Hinton basically is now denounced all of modern NLP as way too dangerous.
Okay.
It should be heavily regulated. This was BBC front page news today. So effectively today. And so more and more people are going to get worried about the way NLP is going. So our advantage is interpretability.
Okay.
We have interpretable NLP. And just for that reason alone, it already has an advantage.
So by interpretable, you mean that you can interpret how the algorithm is working?
You know what's going on inside.
Okay.
You know what's going on inside.
Yeah, exactly.
And these will then also allow you to better predict what's going to happen and what because I mean, Italy, okay, they legalized it, but they banned ChatGPT.
Yeah, I know.
And in Belgium, there was a suicide because of a chatbot buttons, and it's just going to get worse. It's just going to get worse. So I mean, I've been talking to a partner, a business partner. I'm not going to say the name, but it's a bank, and the financial regulator doesn't allow them to use these things because they don't want some completely unpredictable AI to cause the next financial crisis.
Yeah, for more serious tasks, I think the use of this kind of classical models is still questionable very much. I mean,
yeah, there's more and more voices coming up against. Now, Jeffrey Hinton is the father. He's the father of all of that. He invented the stuff, and he stood up against it now. He resigned from Google.
Yeah.
So that's news from today. So yeah, so this is a second advantage, the interpretability, besides the quantum advantage. And for the reason of interpretability alone, people are going to be very interested in this sort of new way of doing natural language processing.
Yeah, I hope so. Thank you very much.
I hope so too.
So I have a question, Bob. So far as I remember, like from 13-14 years ago that I worked with you, like how different is the ZX calculus from, I think, GHZW calculus that we were doing? Is that somewhat?
Okay. So that was interesting. So of course, first we had ZX calculus. We first had ZX calculus, and then we also came up with this ZW calculus. This is what you did your master thesis on.
No, mine was on GHZW calculus. GHZ and W.
Z and W, you, huh? Yeah. Z and W, yeah, no, I remember. And then so it looked very attractive, this Z and W calculus, because of the fact that you could encode arithmetic into it, which was part of your thesis, that you could encode arithmetic into it. But practically, it never came to much use on its own. Okay. And it's just recently that somebody realized that actually Z, X, and W, they all work nicely together. And you can throw the three together. And that's what so suddenly we were able to integrate, differentiate, exponentiate, doing Hamiltonians and all that by throwing the three together. So that's a very reason, and we have proved completeness in all dimensions. All finite dimensional, we've got completeness now. And again, we're writing a book at the moment. We're writing a book picturing quantum optics or something like that, because ZXW is the language which the photonic people really need to use and want to use.
I see. Okay.
But that's quite a recent development, this realization. It's been this realization that actually you can throw a W into the ZX mix and it still stays nice. I thought it would become super ugly, but it didn't. It stayed nice.
Okay, that's great. Anyone else have any other question? Bob?
Yeah, I have a question.
Yeah, Prasanna.
This may be more of a naive question, but this has to do with the quantum circuit optimization using ZX calculus. So if my understanding is correct, then you have a quantum circuit which is then recast in terms of spiders. Then you do the manipulations and then you recast it back to the optimized quantum circuit, right?
Exactly, yes.
So as the system size increases, or in other words, as the circuit size increases, how does the cost of doing these transformations scale? Because that would sort of be of practical importance, right? That the transformations are not costly.
I mean, it's a problem we don't entirely understand yet, because the last step, going back to a unitary circuit, turns out to be, in principle, really hard. But in practice, we have come up with certain strategies which always give a good result. We don't know if it's optimal. We don't even know if it's optimal what we're doing, but but it's the best in the world. It's the state of the art, but we don't know whether we're optimal yet. So there's quite a few open questions there. Like I said, in principle, going from a ZX diagram to a circuit is a really hard problem in principle, but in practice, with our strategies, is not. So it's a very good question. It's a very good question, and there's a lot of open questions still there.
Okay, thank you.
So Bob, one more question. You mentioned about Quantoven, right? So is that like a basic prototype thing, or does it use Lambic full scale?
It's a self-standing thing, but a lot of it just came straight from Lambic. It's a thing which exists on its own.
Okay.
It's a software which exists on its own. It's also out there, open source.
Mm-hmm. Okay.
But it exists on its own.
Right.
I mean, a lot of it was just copied directly from Lambic.
Right. But it's used for music processing, right?
Yeah, I mean, yeah. So the IBM people also worked on music and stuff like that. And there is actually now, it's interesting. There is the last, I think it was 2 years ago, there was like effectively a first conference on quantum music, quantum music. And I think the next one's going to be in Berlin, I think in October or something.
Okay.
And there's actually one at ICFO, like the optics in Barcelona, the optics lab where Tony Yassin and Levenstein are. They're organizing a workshop on quantum music, so I'll be there in that's in June, I think. So people are starting to do this more.
Right. So anybody else in the audience, Prasanna, anybody on the YouTube chat box, maybe asking any question for Bob? Can you check?
I don't see any questions yet on YouTube.
Okay. So anybody in the audience here, like on Zoom, do you have any question for Bob? Okay, so Bob, one more question I had. I saw a recent post from you that you were actually considering using this picture language for exploring consciousness. So that seems like a pretty big thing. What's this about?
So basically, there are already a couple of papers out there where people use ZX and ZW for consciousness. It's been going for a couple of years, and this is people in the Department of Mathematics in Oxford, and also some people who were in my group. They basically started to come up with a community which is called Mathematics for Consciousness. Now, most of the stuff is not consciousness; it's cognition, which is easier. But there are some people. We had a conference 2 weekends ago. 2 weekends ago, we had a big conference in Oxford. There was 80 people.
Okay.
For a 2-day workshop on consciousness. No category theory for consciousness. Only category theory for consciousness, nothing more. And I think it was 80 people.
Okay. All right. Yeah. So no more questions from the audience? If not, thank you, Bob, for this excellent talk. And we look forward to having more talks from you.
Okay, thank you for having me.
And yeah, you do you do come to India sometimes, right? For to meet your collaborators?
I mean, I've been in Calcutta once.
Yeah.
Couple of years ago, I was there.
Yeah,
the Indian Statistical Institute, I think.
Yes. So if you do come down to Kolkata, do come to visit our center. That would be great. It would be great to host you actually. So yeah. So, all right. So I think that's all for today.
Bye, everybody. Thanks for having me.
Yeah.